Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth.
Hello, folks. Today we are joined by Dr. Jack Drummond to discuss moons orbiting asteroids, adaptive optics, and why astronomy is known as the Queen of Sciences.
In 3, 2, 1.
Hey, folks. Today we are joined by Dr. Jack Drummond, who's had a long civil service career and is now a contractor to AFRL from Leidos as an astronomer. Thank you for joining us, Jack.
Oh, thank you for having me.
So, starting things off here, we have to ask you. So we've heard that you have an asteroid named after you, and we're wondering, first, how does that happen? And second, can we get our name up there, like a Lab Life asteroid? Is that an option?
Well, I'll tell you how it goes. Comets are named after the discoverer. So you have Comet Kohoutek or Comet Linear, which is named after a facility. But asteroids are named by the discoverer for somebody else. So there's a handful of astronomers that are doing all the discoveries of asteroids, and then fellow astronomers will appeal to them, asking them, will you name this asteroid after my colleague? And that's what happened when I was at the University of Arizona. I had done about 10 years of research on asteroid light curves, and one of the colleagues who I was working with nominated me for the name of the asteroid, and I got it. And as I say nowadays, that not many people know this, but I'm famous. I have an asteroid named after me.
No, that's a big deal. You're right. I would honestly, that'd come up in conversations more for me, but that just may be who I am. Hey, I'm pretty famous, right? I've got an asteroid up there. Pretty cool stuff.
Right. Well, that was also supposed to be funny. How can I say not many people know this, but I'm famous?
Yeah, that's what I'm saying.
Well, after this podcast, surely you'll be famous. So.
Right.
But that I was going to say, that's great to know, though. So at least you laid that out for us, so we know that if we get more news, get to know some more astronomers here at AFRL, maybe it'll be the case that Lab Life or one of us can get up there with you and maybe be even a fraction as famous.
Yeah, that's right. It happens. And by the same token, I nominated Bob Fugate for his asteroid name based on the work that he had done. So, if you chum up with me, maybe I'll nominate you.
Hey, you know what? We'll see what works out here. Either way, we're glad to have you on the podcast, Jack. So taking a step back then, speaking of some great astronomy stuff and kind of diving into our subject today, what really got you interested in the stars, everything moving around up there?
I think it's a natural consequence of being young. I think every 12 to 13-year-old develops an interest in astronomy, and with me, it just stuck. In particular, I started subscribing to Sky and Telescope magazine, and I now have a 60-year subscription going. It's still continuing, but every month I look forward to that issue, and I would take a pair of binoculars outside that my father had put on a tripod and study and look at the things that I could see. So I've always had that interest, and it stuck with me through college and graduate school.
I think you're right. You just took me back to some times in Girl Scout camp where we went out into a field because a remote site had some good night sky, and we're looking up there trying to identify some constellations, and if we were lucky, maybe a planet. Really cool.
Yes, and one thing that is common among students is going camping with their parents and watching a meteor shower, because Perseid meteor shower, which is the biggest of the year, occurs in August, and a lot of kids are outside and they get to see a meteor shower. In fact, that was my first interest, was meteor showers.
And that's an interesting thing you brought up here, and a lot of people may not fully know that. So with enthusiasts looking to kind of dive in the field, you mentioned that when you were younger, you just had binoculars yourself before you actually bought a telescope, and that kind of worked for seeing some heavenly bodies?
Yes, I've never had a telescope. I had binoculars which give you good views of comets and nebula and objects in the night sky. Now, not planets. It's not high magnification thing. It's you can't see the details on Jupiter and Saturn, but you can see Jupiter's moons. And I eventually was able to find Saturn's moons. So there are projects you can do with binoculars. I found it much more comfortable to view celestial objects with two eyes rather than one. And just a pair of binoculars is there's a lot you can look at. Also, naked eye. There's meteor showers and eclipses, and comets can become naked eye. So you can be naked eye or just a pair of binoculars before you move up to binoculars or higher.
And I think that's a cool way of kind of showing people that, especially when I was younger, I went to planetariums, saw these massive telescopes, and went through great displays to show the amazing worlds around us, but never knew how accessible it really was. That, like you mentioned, if you have the right tools, even some like high-powered binoculars, you can see some cool stuff. So this is really accessible to people who may have to step away from the light pollution of the city, but there are options out there.
Yes, that's right. Yes, one of my favorite things was hunting down galaxies with a pair of 10 by 50 binoculars right on the edge of visibility. I was just stunned the first time I could identify a distant galaxy in my little 10 by 50 binoculars. And that just piqued my interest.
So I want to touch on something you mentioned too. Speaking of interest, with Sky and Telescope magazines, since you've been collecting them, you've been a fan for so many years now. Is there any particular issues that may have had a pair of binoculars you used, or had a really cool like tip or trick that you still to this day thank for kind of helping your love of astronomy?
Well, I just enjoyed reading the issues and the upcoming events. And I do have to say that in March of 1963, when I was a senior in high school, I actually had an observation report that I submitted that got published, and that was a big thrill. It was about a penumbral eclipse viewed from my high school in Hialeah, Florida, and it was very gratifying to see my little report about the copper moon sitting on the horizon with its entire left hemisphere subdued orange. And so just getting my name in print like that, and even though my friends didn't even know about it, it was a thrill to me.
I mean, certainly. I mean, to be a high schooler and published in a national magazine, that's pretty cool.
Yeah, once again, I was famous even though nobody knew it.
Right. Well, you said astronomy is a pretty small field. You said there's about 4,000 or so folks.
4,000 professional astronomers, right? A lot of others working in the field, like instrumentalists or theoreticians, but professional astronomers making their career in astronomy, there's about 4,000.
Yeah. So perhaps famous in your circle, I would imagine.
Yes, I guess so. Although they're all famous too.
Well, so you mentioned you went to high school in Florida, but you ended up at the University of Virginia in the ROTC program, and then you joined the Navy. What can you tell us about that experience?
Well, I went through University of Virginia with a ROTC scholarship, so that was pretty important to me because that allowed me to major in astronomy. As soon as I graduated, got commissioned and went off to Pensacola to flight school. And so for the next 5.5 years, I matured, let's put it that way. My undergraduate cumulative GPA was only 2.2. So I was a serious student, but not a very good student. And I took the advantage of being in the Navy to mature. And when I finally got out of the Navy and I applied to graduate school, got accepted in New Mexico State. So I would say that being in the Navy was a maturation process.
That's important for a lot of people, especially going through university. As you mentioned, you always need that catalyst or something to really help you. For some folks who say, hey, like I want to make sure I have things like lined up in order, so I'm ready to finish this and follow your passion. So I'm glad to hear that could be that force for you.
Yes, and it was a good life experience too. I went to Vietnam to fly, flew out of Saigon, Da Nang, and then Korat, Thailand. And all that's pretty serious and pretty heavy, and it prepared me for graduate school, perhaps more than my undergraduate school.
That was something I wanted to touch on was pilot training, I should say. Like, is there anything from pilot training or being up there multitasking in the skies that really prepared you for being an astronomer? Like you mentioned, even just preparing you for life or later in life, excuse me.
Well, I think it built my confidence. I was a pretty shy kid growing up, and at the University of Virginia at that time, it was an all-men's school, so I had no social life, didn't even date really. And by being in the Navy and being pilot and making those decisions, I really did grow and gain confidence so that I went into graduate school confident.
Hey, and I'm sure after that point, made a lot of great friends and great connections. So it's cool that could give you that confidence, or give you more of that gravitas you could carry forward.
Yep, and it taught me to focus too.
Definitely, I can imagine. And something that's cool about being out there in the ocean, then, especially in the Navy, I have to imagine without any light pollution or any cities near you. I mean, the night sky had to be beautiful. Like you'd have almost an unfettered look into the cosmos.
Yes, especially when I was a midshipman, we took cruises across the Atlantic. And in the middle of the Atlantic or the middle of the Mediterranean, the sky was completely dark with no lights on the horizon from any city. And it was pretty spectacular. That was a good place to see meteor showers. And on more than one occasion on the bridge, we had people calling out an unidentified object coming at us, getting closer and getting higher, and it was red on the horizon, and it inevitably turned out to be Mars. Mars sitting on the horizon can be spectacular and scary and unprecedented for a lot of people on the bridge.
Oh, I got really excited. I thought you were going to say you may have seen something unexplained. I wasn't sure if you had made any connections while you were out
Well,
there.
I had to explain it to him. It was just a planet horizon.
Still, it's great they had you there, honestly. Otherwise, they may have had quite a different story to tell.
That's right. They might have started firing at it.
Yeah, see that? Good thing you said, hey, guys, hold on. I know what this one is. That's fascinating, though. And again, the fact that you had a chance to really see that, and being a midshipman, getting able to see a lot of the night sky out there and having that access to it. A lot of folks now, like we mentioned earlier, they have to go pretty far out, like either going out to the country, specific locations, just to get kind of a look like that. So that's really cool.
Right. And once I got to into graduate school, Kitt Peak, for instance, south of Tucson, provided the same view. Although the sky glow from Tucson was in the northern horizon, it was a dark sky. And then even better, once I started observing at the main observatories, the big observatories in Hawaii, from 14,000 feet, it's pretty spectacular too. You actually feel closer to the stars. So on the open ocean, the desert Southwest, or mountaintops, spectacular views of the sky.
So I'm glad you mentioned going off to graduate school a few times too, and getting this new look into the horizon, if you will. So speaking of your career horizons, we know you went to a New Mexico State University to receive your PhD. What was the area you focused in specifically?
My dissertation was in planetary nebula because I wanted to study asteroids. I'd already developed an interest in asteroids, but they already had someone going through. It was a brand new department. I was only the 9th PhD to get a PhD from the school. So I was not allowed to do my dissertation on asteroids, so I picked planetary nebulae. But I had a colleague at Tedesco who I observed with. We observed asteroids, and that ignited my passion for smaller objects of the solar system.
And for those of us not as educated in astronomy, what is planetary nebulae?
That's a star that's blown off its atmosphere, and we now see it as a not a point source, not a star, but as a circular blob that you can actually resolve. They emit very specific stellar lines, spectral lines. I studied them to see if any of them are binary for the reason, as a reason for them blowing off their atmosphere. It was pretty simple, pretty fundamental, but already my passion was into asteroids.
And that's what's interesting is I know a lot of people always talk about being astronomers for studying planets, different moons, even exoplanets. And a lot of folks don't really think about the stuff in between, like you mentioned, things from asteroids, things like comets, like different space debris that really fill in a lot of the space, but usually don't get a lot of the highlights until one passes close to Earth. And someone you mentioned is like, hey, this object's coming by, look for it in the night sky. And I mean, that's awesome, but it's usually something I don't hear about.
Yes, and I developed that interest when I was one time as an undergraduate, went to the Hayden Planetarium in New York City, picked up a little book called Between the Planets by Fletcher Watson, and thumbed through that. And that's where I really said, what the heck are asteroids? Asteroids are little rocks between Mars and Jupiter, most of them in the main belt, but they have light curves. That is, they vary regularly over time in brightness. And I could not figure out why. So I took that interest back and started to work out the equations on why an asteroid would have a regular light curve. Sometimes it's a high amplitude, sometimes it's low amplitude. It all depends on the geometry of your observations. And so I started developing the mathematical equations. And one of my first memories, too, is in high school from Sky and Telescope, tracking Pallas, which is the second asteroid discovered, underneath Orion. So night after night, it would move a few degrees, and I would track it on my little map. And I was just amazed again that I could see asteroids with my binoculars and actually map its path in the sky. So I've always been fascinated with them. And then also the meteors, that's another small between the planets, objects between the planets. One of my first observations was staying up to look at the Perseids early in the morning before school and just being blown away by the light show that it produced.
And thinking of a lot of those small objects too, I mean, something that I know has come up, especially in the asteroid belt, is how sometimes that micro can be very macro. People don't really appreciate how big a lot of these things are. And I know there's that whole debate about Ceres being, a dwarf planet and everything, like being supposedly a planet at one point. People were debating if it should join the roster because it's there between Mars and Jupiter. It's pretty big, but I know I can't remember now. Is it dwarf planet or is it just a large object?
No, you're right. It's the only dwarf planet that isn't out by Pluto. It's a dwarf planet right smack in the middle of the asteroid belt. It has more mass than all the other asteroids combined. So it is a big planet. And when it was first discovered on the first day of the 19th century, January 1st, 1801, it was declared a planet, and it was the missing planet because it fills in the spacing between Mars and Jupiter. It follows the sequence. But after a while, they start finding other objects in there, not quite as bright, and realized it was a new kind of asteroid. And then, of course, once Pluto got demoted, because it's not the biggest one out there, there are others just as big, and they designated Ceres as a dwarf planet. It's sort of interesting, the things that I've studied here at Starfire are the satellites around asteroids, moons around asteroids, but they're pebbles around rocks compared to Ceres. Ceres and the other big guys, the giant asteroids, are large, but they have no moons. So the moons only seem to appear around smaller objects and not the big guys.
Well, you just mentioned something our listeners might not be familiar with, the Starfire optical range at AFRL's location in Albuquerque, New Mexico. Could you tell us a little bit about Starfire?
Well, Starfire, I consider, if not the birthplace of adaptive optics, is the cradle of adaptive optics. Bob Fugate had a classified military experiment going on here, trying to apply adaptive optics, which would achieve the resolution of the telescope. And when he declassified it, then I got hired. And since then, we've been using adaptive optics to study asteroids and moons because they are good surrogates for satellites, man-made satellites that get close to each other. The good guy, bad guy scenario, where you have a little snuggler sneaking up on one of ours. We want to see what's going on, how close it's going to get, what its trajectory might be. But we can't study those kind of man-made satellites because no satellite operator is going to let another satellite come near it. So instead, we look at asteroids and the moon. They're about the right brightness or about the right distance. And that helps us perfect our techniques for resolving these objects and determining their orbits. So that's one of the many things that adaptive optics is used for. Once Bob Fugate had his experiment declassified, he turned it over to astronomers and probably saved the astronomy community 10 years of research. And now every large telescope in the world has adaptive optics on it. All started here at Starfire.
That's pretty amazing. And Dr. Fugate's also a Lab Life podcast guest, so our listeners can really tune in to hear even more about his story. I love
he'll fill you in. Yes, that's for sure.
Oh yes, he's fascinating, brilliant man.
And that's so we touched on a lot. We've brought up the adaptive optics. Now it's changed everything. And I think you may have mentioned it, but just to bring it back to a head, there's a really cool quote we had from you. We kind of had a conversation before this where you mentioned that adaptive optics is really the biggest change in astronomy over the past 400 years. So I as somebody who's out of the astronomical game, if you will, had no idea how big it was, but I've been taking it for granted for most of my life because I just assumed that's how things always were, at least for a while.
That's right. I think it's the most innovative breakthrough since the invention of the telescope itself. The atmosphere pretty much limits observations of stars or objects in the sky to about 1 arc second, all about the same size. So the atmosphere blurs all these point spreads, point functions, to the same size. But with adaptive optics, you untwinkle the atmosphere, and now you get stars look like point sources almost. So the larger the telescope, the better the resolution, except for the fact that the atmosphere limits all telescope resolutions to the same size. Turn on the adaptive optics, now you can achieve the resolution of the large telescope. Larger telescopes will have better resolution now.
I'm just sort of wondering, we kind of touched on adaptive optics. Is that what you spent most of your career at AFRL focused on? And what year did you start with the research lab or one of our predecessor organizations?
In 1991, Bob Fugate hired me, and I got hired right into the adaptive optics section. And that's all. That's what we've done. We've specialized in adaptive optics. Not only were we the first to publish articles with adaptive optics, we also, the Starfire Optical Range, developed lasers, and they were the first to use the lasers, which helps adaptive optics. It provides an artificial point source in the sky, in case there are no stars nearby, where you can then look at objects. So, for instance, if the asteroid were too faint, you can use a laser and make a point source and close the adaptive optics loops and make resolution better. So we've developed not only adaptive optics, but the lasers to go with it.
So I'm wondering, what does that look like? You're out at the Starfire Optical Range at Kirtland Air Force Base, this big AFRL facility, and you're shooting some lasers into the sky. What does that look like, to those of you on the team?
Well, if you're right behind it or under it, like we are at the observatory, it's pretty spectacular.
Yeah, that's something I was trying to visualize in my head. Being a big Star Wars fan, you can imagine where I jumped to here
Right.
about high-powered laser, and to hear that not quite Death Star level, of course, where it's massive and visible from anywhere. It's cool to think that even like you said, a mile or so out, like it can kind of fade into the distance. Like you have to be
Well,
closer, but
yes, and it's not really a high power laser. It's only maybe 50 watts,
oh,
and
interesting.
we take extreme precautions, safety precautions. We don't shoot it up if there's any airplanes in the sky. But if an airplane were to go through it, they probably wouldn't even notice it. It's just not that powerful. I suppose there's somewhere they're developing lasers to shoot down planes, but it's certainly not our laser.
Wow, so retooling in my head then. So I imagine having to have this almost like the guide stars you mentioned. I thought it'd have to be a lot of power. So you're saying that you're able to accomplish these amazing feats, but it doesn't take that much oomph behind the laser to do it.
No, it doesn't, because what the laser does, it tickles the sodium atoms about 90 kilometers up and gets them to fluoresce and shoot back at us. So all we're doing is creating a chemical reaction up there, and we're observing that as a star.
It's wild. I don't think I've ever heard tickling ions in a sentence before. So that's a really great visual.
Yeah, that's exactly what happens.
And something, speaking of your career and the amazing stuff you've done, so I know we've touched on it, but I'd love you to describe this further. So I learned about something new called, I think it's Lorentzian point spread function, something that you helped develop, this breakthrough. So can you describe what that is and kind of what it all entails?
A point spread function is normally modeled as a Gaussian through the atmosphere that is a particular shape. But once you turn on adaptive optics, it changes that shape. And in order to get the most out of adaptive optics, we had to come up with a new point spread function, which I developed as a Lorentzian. And so now if you model that star or an asteroid, which looks like a point source, it's not resolved. So it's a point source coming in. If you model that through the atmosphere and adaptive optics as a Lorentzian, you can subtract that and see what else is around it. And that's how we've looked at the moon. So we subtract the model from the observation and see what's left around it, and out pops the moon. This is exactly the technique astronomers are using to look for planets around other stars. The small planet around another star is lost in the glare of the bright star. But if you can measure and model that bright star and subtract it, there's your little planet. Same principle for asteroids and moons and Earth satellites.
Wow. Like I know we kind of mentioned earlier what your team's doing looking at these satellites around asteroids, which I want to get more into in a second. But to think about the scale of space, like just trying to stretch my mind out there, that when you're out seeing a lot of these asteroids, celestial bodies, I mean, they're massive. But to think you're right, an observation, a speck in the sky, almost non-existent. So the fact that we need this technology to see something so big yet so far away it's just really cool to wrap your head around.
These objects are point sources, though. So even though they're fairly large, they're still point sources to us. Before adaptive optics, no asteroid had ever been resolved. So asteroids were always points of light in the sky that changed brightness, and we had to deduce what they might have been made until we began to resolve them with adaptive optics. And the larger ones can be resolved. I've also studied and published many papers on the large asteroids, resolving their shape and their size and getting their poles and their dimensions out of it. But the ones with moons, like I said before, are small, unresolved. And so we have to calculate the orbit of the moon around the asteroid and thereby deduce its mass, its density, and what it's made of.
And to think we can pull all of that from these observations and, like you said, actually resolving and kind of diving more into the dimensions of these asteroids. I wanted to go in a little deeper with your team then. You mentioned earlier how you guys were studying these asteroids and finding out that they have these satellites around them. So can you kind of go into some of the major findings your team has had and what impacts these could have for the future of either space observation or for AFRL?
Well, they're direct analogy to Earth satellites as far as objects, as far as resolution and developing their orbits. But in their own right, a moon going around an asteroid, and that's what blows me away. Just taking pictures of a moon's going around an asteroid, you can get their mass and their density from Kepler's laws. If you see two objects in space orbiting each other and you know how far apart they are, you can get their masses. That comes from Kepler's laws developed in the 1600s. And so by just taking pictures, we can begin to get an idea of what they're made of. And you can't get that kind of information any other way short of a spacecraft visit. So that's what I've really enjoyed about this. I can observe these objects with the ultimate goal of applying them to Earth satellites, but at the same time publish astronomical papers on their astrophysical quantities.
And that's, I mean, it's kind of putting that in context again, thinking about how small this object is, even smaller than that point in the sky you mentioned, to track that asteroid, like, or excuse me, the satellite around it. I mean, before I read a lot, like the article I saw highlighting your work, I had no idea you could have those orbiting around asteroids. Like, that just seemed too small.
Well, that's right. I'm embarrassed to say that in 1998, at the University of Arizona, I published a paper saying that there would be no moons around asteroids. And about 2 years later, they found one. And after that, they have dozens and dozens of them. The flaw that I made was I was applying it to big asteroids because any big asteroid that had moons around it would have suffered enough collisions to knock the moons out. But the little guys seem to be remnants left over from their last collision. They retained some of their particles, small moons, and now they're pebbles around rocks instead of big moons around big asteroids.
And that has to be such a cool part, or to take part of that history. Like you'd mentioned, seeing that, okay, this is possible. Let's dive deeper into it. And to watch that evolve here over the past few years, I mean, it's so cool to see how, well, minute this can get. The fact, that your team's been a huge part in it. I mean, that's going into work every day and seeing these new photos or like seeing these new,
Yep.
I should say, like seeing everything coming out and finding even newer satellites has to be so rewarding.
Yep, the first satellite around an asteroid, although they had seen them before, the first one was discovered by the Galileo spacecraft on its way to Jupiter. It was going to Jupiter, and all the windows were closed, and some astronomers realized that its path was going to take it near the asteroid Gaspra, and they wanted to open the windows and take pictures of the asteroid because the asteroids had never been resolved. But there was a big argument. Finally, the head of NASA convinced the people who had the instruments headed for Jupiter, they wanted to protect them, to go ahead and open the windows and take a picture of an asteroid. So the first picture of an asteroid showed a moon around it. Stunned everybody. And after that, since then, asteroids have been discovered with adaptive optics. It seems like you just look at the brightest asteroid that's up at the time, turn on your adaptive optics, and there's a moon. And that's what happened with this last paper I published on Olympias around the asteroid Roxanne. I was with the team in Hawaii, the Gemini telescope, and one of our colleagues simply looked at the brightest asteroid every night to look for moons, while I was looking at larger asteroids, measuring their sizes. He would swing off in between, look at a bright one, and by golly, got one on that first night, and that's the one we finally published an orbit on. So we discovered it, published its orbit, and published a paper on it. And all that is pretty exhilarating and gratifying.
Absolutely. That's super exciting. I mean, just for it to happen like that had to be even a bigger thrill.
And when I found out that the large telescopes, the 8 and 10 meter class telescopes in Hawaii, were discovering asteroids, moons, just by looking, I wasn't sure whether our small telescopes, only 3.5 meter, could even see one. So I convinced our local people to go ahead and look at an asteroid with a known moon. And by golly, it was there. But it takes a lot of work. I mean, the people we have here are pretty darn sharp. Odell Reynolds, he's my primary observer. It's a combination of magic, art, and science. He can just make that telescope and adaptive optics hum. And he pulled out that first satellite around Sylvia. And we followed it and derived an orbit. So I said it can be done from here. And now we're on our third satellite around an asteroid, and we'll be looking for more since we can't study man-made satellites.
Yeah, well, and maybe this is a good transition point. If you could explain, why does the AFRL care so much about this far out there research? To throw in a pun, Ken likes puns.
They aren't interested in necessarily asteroids themselves. I am. I think it's fascinating, but it applies directly to our man-made satellites. Like I said earlier, if we have a little, let's call him a red guy, sneaking up on one of our blue guys, how close can he get? How close will he get? Well, with the techniques that we've developed here, such as the Lorentzian point spread function, subtract it out to show the little guy. The only way to apply that and to use it and to study it is use the proxy. Asteroids, moons around asteroids. They're about the same relative sizes. They're much further away, the asteroids are, but they're the same angular sizes, and they do about the same thing. They go around each other, they go near each other. And so the techniques that we're developing here, both to observe them and then to plot them and to derive their orbits, are exactly what would happen if we were able to study closely approaching man-made satellites. But again, telescope operators aren't not going to allow anyone near them. There's billions of dollars of investment. They don't cooperate and say, okay, we're going to have two satellites fly around each other. That's just not going to happen. So we go to asteroids and moons. Perfect proxy.
That makes sense. So the military application of it, and then also you don't have the dollar risk of, let's fly some really expensive spacecraft near each other, and just so we can see what might happen.
Exactly. And not only that, these satellite operators don't want to shooting lasers at them, even though it's not very powerful. They don't want to have lasers pointed at them. Now, asteroids don't care.
And it's what's interesting about that too is thinking about the logistics of checking out this object hurtling around here, man-made and as small as it is. Like it does almost seem more difficult than tracking an object like an asteroid. So hearing that the relative size, like you'd said, at least in terms of viewing from a telescope, is similar is something I had no idea. So what a great way to train for that, like you mentioned. In case something were to happen, you guys would have the right tracking at least to find out. Okay, we can better have an idea if an object is getting closer, especially near Earth orbit, to another satellite. Like I didn't realize that could be connected.
Yes, and one difference also between the man-made satellites and asteroids is asteroids are slow-moving, so you can follow them night after night. Man-made satellites go around the Earth in about 90 minutes. So we have a telescope that can move 11 degrees a second across the sky. So we can actually chase man-made satellites, and then we slow down our technique to look at asteroids a little more leisurely. We can do a little more research and development on it. It's a time-intensive experiment when you try to do something like that on a man-made satellite going across the sky.
I can imagine again. So that really does show just how quickly it is orbiting the Earth. So the fact we have the right stuff in place, or you mentioned it, at least having a right telescope that could scan that or follow it, that's amazing. Then we have a development that can track it that fast. Because I was going to ask with asteroids then, yeah, with them moving across the night sky, is there an average speed as to which they go? Like you actually do see them do a full across the night sky, like you can track for 30 days or so before it goes over the horizon?
You can track an asteroid for about 3 months. And
wow.
When it first appears in the morning sky, it's fairly faint, and then it gets overhead at midnight and it's at its brightest, and then it gets into the evening sky and it gets fainter again. So it's closest, brightest overhead at midnight, and it's about a 3-month process. So during that time, I've already demonstrated with a couple of our asteroids, you can watch the moon go around the asteroid in one, what they call opposition or apparition. In one apparition over 3 months, you can develop and find its orbit. So that's pretty significant for astronomers. Also, another advantage we have here is that we're not a field telescope. We're not an operational telescope in the sense that at the large telescopes like in Hawaii, they lock down the telescope for a semester, and it's highly competitive. Everyone competes for time. And if you get time, you're lucky to get 2 nights on it. And you can't do a satellite around an asteroid in 2 nights. But here, I simply ask Odell Reynolds or one of the other guys to just look at my asteroid every night for 60 days, and then we can get an orbit. So we can do things here with the asteroids that you can't do at the major facilities that are designed for astronomy.
Well, that just goes to show what resources that the Starfire optical range, what we have here, to actually, like you said, have spend more time with these celestial bodies and make sure that we get a full idea of, like you said, size, where they're going, speed, and if they have those satellites. So I didn't realize how much time it took to really gather this information, or at least how long we had to gather it.
It's been a real boon working here. I mean, it's pure research. When I left the University of Arizona, I was frustrated, trying to survive on soft money, that is, on grants, and only 1 out of 5 grants would ever get funded. I never got any. I always had to be tacked on to other people. And then I came here to the Starfire Optical Range, and I didn't have to worry about deadlines and proposals or anything else, just pure research, as long as it had a relevance to the Air Force. And I have been extremely fortunate for 30 years to work here in Albuquerque at Starfire Optical Range, originally with Bob Fugate until he retired. And now it's still a special privilege. Now that I'm semi-retired, I can pick and choose the projects that I want to work on.
And probably pretty exciting too, as we, support the Space Force mission too. A lot of, that AFRL's one laboratory serving 2 services. So a lot of the mission out there and directed energy and space vehicles is focusing on the Space Force mission now.
Absolutely, and I can see we're aligned perfectly with that. One of the things about studying asteroids is you can, like I said earlier, get its mass and its density, figure out what it's made of. That's for the main belt asteroids, but there are a lot of asteroids that come near the Earth, between the moon and the Earth. And if there's ever a potential impact or a flyby, we can study it. And it seems like quite a few of these near Earth approaching asteroids are also binary. We can watch the moon or watch them go around each other, derive the density and mass. And this leads directly into the Space Force. If we see there's going to be an impact, maybe the Space Force can do something about it. We know that they're going to have to disrupt or destroy an ice ball or a rocky asteroid. So it's good to learn about the asteroids near and far, and the Space Force, in my mind, is also going to help protect us from them.
Well, certainly one of the things that I don't want to stay up at night worrying about is asteroid impact to the Earth. I mean, I'm glad that you and a lot of other astronomers are out there kind of looking for these asteroids that aren't just nice in their space belt between Mars and Jupiter and are actually in Earth's orbit.
Yes, so we've discovered about 95% of asteroids that are going to come near the Earth that are larger than 1 kilometer. Smaller ones we can probably withstand, but if they're larger than 1 kilometer, it could be catastrophic. We discovered about 95% of them, but that still leaves 5% that one day will pop up and its head is straight at Earth. The only warning we'll have is on its inbound leg. We might have 3 days notice, and we're going to have to do something. And we can't stick our head in the sand. It's going to happen. Look at the moon. Look how much the craters you see on the moon are not volcanic craters, they're impact craters. That tells you how often the Earth is going to intercept and be impacted by asteroids. It's just their size that matters. But we can't just stick our head in the sand. We have to be prepared. Space Force is a logical extension of our defense.
So you said that we tracked 95%. Is that known just by the asteroids that have passed by? We've checked multiple times and we've okay, we know this one's expected to come at this point, and that's how we've mapped out the current known ones, or how does that work?
Well, there's about 1.5 million asteroids known, and
Wow.
by that we mean known to the point where we have the orbits, we can always predict where they are. But we've discovered, once you discover an asteroid, you can make an estimate of its sizes, and so you can develop a size distribution. And you can see that we've discovered it's plateaued. All the asteroids that come near the Earth larger than 1 kilometer, or 95% of them. Anything larger than 2 kilometers, it's 100%. So something like that. So you can develop models from the ones that you have discovered. You know where they are. But like I said, for larger than 1 kilometer, there's still a possibility someone's going to sneak up on us and not give us much notice. One of the big guys.
Well, maybe I will lay awake at night worrying.
No. We've been on Earth 1 million years and we haven't been destroyed.
That's good, because I have to say, not this podcast, but talking about worrying, we interviewed some epidemiologists right before the COVID-19 pandemic in 2019. And then, they had me worried about novel viruses, and then this happened. So I just don't need one more thing to worry about that I can't control.
Well, yeah, I see your point, but don't forget the dinosaurs were wiped out by an asteroid or a comet, and there's been several mass extinctions throughout history, mostly all due to asteroids or comets hitting the Earth. But things seem to have quieted down. I mean, part of the reason why so many collisions have occurred previously is because the whole solar system was being formed. Now it's fairly stable. It's quiet. Life has been allowed to evolve and expand and exist. We're not in a violent solar system anymore.
And I think that's where it comes in too, that if we do have a high-powered laser beam, that's where we can actually start using it.
Yes, there's the various ways to do it. Another interesting way is just to fly to it, put a giant sail on it, and the solar radiation pressure will nudge it off its orbit, and it'll miss us. So there's various ways to do this.
Yeah, I think that's a safer way than mine for sure. I was thinking Armageddon too. Like I've seen a lot of different films and ideas of how to deal with it, but that sounds like well, I mean, honestly, the logistics still a lot of different moving parts to it, literally. But it sounds like a safer option.
And another option too is if we're going to go to Moon and Mars, we need resources. Asteroids are great resources. I predict that in 500 years, we'll be getting most of our resources from the main asteroid belt, metals, even water. Ceres, the largest asteroid, is full of water. It's just underground. And we'll need stations out there to get the resources. Also, these asteroids that come near the Earth are another source. We'll simply fly up. They'll come around every 3 or 5 years. Fly up, say, mine them, store them, and the next time it flies by, get those resources down to Earth. So there's another reason to study asteroids, especially near asteroids, and that again will have to involve the Space Force.
Just very interesting. I mean, I've heard people talk about could we mine the moon for its resources, but I didn't think about landing on a asteroid or lassoing an asteroid. I don't know what exactly I'm picturing in my head, but that's
pretty close, yeah.
We'll see in 500 years what it looks like.
Well, sure. I mean, they're almost all pure. That is, they have been differentiated. They've been heated up. Metals and elements have been separated into layers, just like on Earth. You find a gold layer, say, and that's what you mine, or an iron layer through the Earth. The same way on the asteroids, you can find one that's mostly nickel or mostly uranium and mine it and get it back. So the asteroids are like broken up pieces, so we don't have to blow them up. They're there exposed.
Yeah, I've heard different people conjecture that. I remember I mentioned to you before, Dr. Drummond, that I'd read that there's some asteroids out there, depending on size, that have like almost the equivalent amount of iron we've seen in our a lot of human civilization. Like we could go up there and harvest even just a couple by lassoing them in, pulling them to near Earth orbit or whatever, and working on that. And that's the idea of building starships and things in the future, actually building in space because we have all these resources. And it's wild to think it's relatively closely in our neighborhood if you get to it, but still out there. But it's attainable here, like you said, the next 500 years, hopefully.
That's right, and it actually takes less energy to get some of these asteroids to come near the Earth than it does to go to the moon, because they're moving so slow with respect to the Earth. So it's all feasible. It can all be done, and I say in 500 years we'll have 10,000 people in space, mostly miners, sending resources back to the Earth.
That's a cool future. Like honestly, my mind's starting to spin thinking about all the logistics of this. But kind of pulling us back here to the modern day, let's say that folks are looking to kind of follow a similar career path as you, like looking to help think about these things in the future, look at the stars, and become awesome astronomers. What advice do you have for these university students or even high school students, kind of listening to this podcast, feeling their dreams like, hey, this might align with what I'm looking for?
Students should concentrate on math and physics. And then pick another subject too. Astronomy has been called the queen of the sciences. Every scientist, no matter what field, should keep aware of what's going on in astronomy. Geologists, biologists, engineers, they should keep abreast of astronomy. And then when they get to their graduate school, they'll be well prepared, because astronomy is more than just looking at stars. It's a wide open field that allows a lot of other fields in: astrobiologists, astrogeologists, and just building of the instruments, building space instruments to go on spacecraft. There's just a wide open future for anyone who wants to include astronomy in the resume. And stick with it. I mean, like I said, I was didn't have a great GPA, but I knew my astronomy. I maybe struggled in math and physics, but I knew my astronomy, and I just kept with it. So if you have a dream, follow it.
Certainly. And what a journey you've had from taking some binoculars outside as a kid and watching meteor showers to operating a one of a kind Starfire optical range.
Yes, I've been very blessed and fortunate in my career. Like my wife has said, Jack, you've done everything you've ever wanted to, and she's right. I mean, I was an astronomer, a pilot. I came here, did research, and had family, and I've been happy. I have no complaints in my life. I have to honestly say, I've never had much stress in my life. I've always been fortunate and blessed.
Well, we're so happy you could join us, and hopefully this podcast is another feather in the cap, if you will, to help talk to people about saying, hey, if you want to know what I do and the cool stuff I've done, check this thing out. So hopefully we can help get your story out to more people, because it's been such a pleasure to speak with you today.
Well, thanks for having me. It's been good to express my view as a man on the hill looking back.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.